Got that going. All right. Here we are. Man, I know I just woke up like a few hours ago, but I'm ready to go back to bed. Winter just messes with me. Does it mess with y'all? It's too cold, and I mostly don't like it when it's super cloudy and no sun. We got sun today, so I think I'll be able to wake up. Okay. Let me see what we got. Okay. We got a few more reactions we have to do. Let's look at our slides really quickly. All right. Going to chapter 10, going to try to finish that up today. And then we'll spend the class period on Thursday working through the quiz. How's that sound? Okay. Let's see. We need to look at, let me see which number. Carbocations. We talked a bit. We got to do the addition. Markanov's rule. I think we started to talk on that. Electrophilic addition. We were talking about this a little bit. Markovnikov's rule. Okay. I think we talked a bit about that already. Okay, energy. So the faster reaction is going to give us the lower energy involved. Okay. All right. Have we talked about electrophilic addition? Or have we only talked about substitution? Degrees of unsaturation. Okay. Let me go back to here. Okay. Where are the degrees of saturation? Is that in? Is that? Oh, the very first one. My eyes are just crossing. Okay. So yeah, we've got to talk about the addition reactions and hydrations of alkenes. Okay. Oh my gosh. All right, electrophilic addition. All right. So let's put this into basics, into words that are easy and a little bit more accessible. Okay. So the Hammond's postulate and electrophilic addition. So essentially all this is saying is, okay, I'll just, since they have a name on it, Hammond's postulate with electrophilic addition. Okay. So when we're talking about electrophilic addition, do y'all remember what that means? When we're electrophilic addition? So electrophilic is electron loving addition reaction, adding reaction. electron loving adding reaction. So we see this with double bonds, right? Double bonds are electron rich. Because if you've got like a 2-carbon bond here, something like this, right here, we have 4 electrons caught up in here in a very close space. So we tend to do addition reactions with double bonds. Now, how we take that with Hammond's postulate, we look at the energy cost for the carbocations and how that plays a role in reaction energy. So, primary, so we've got carbocations. So that's basically a positively charged carbon in a molecule, right? So carbocations, positive charged carbon in a molecule, we have primary and secondary. Primary looks like this, secondary looks like this. Primary would be something like this. And let's put an R group here. Put an R group there. 1, 2, 3, 4. Primary, secondary looks something like this. I'll lay it out like this. Hold on, am I doing that right? Primary carbocations. Am I doing that right? Would be on the end, so it'd be attached to 1 carbon. Okay, yep, I'm doing that right. So this is attached to 1 carbon. This one's attached to 2 carbons. All right. Secondary, the faster reaction. Because lower energy. This one is a slower reaction because higher energy. This has to do with the stability. So, primary carbocations have less stability and are higher energy. So, maintaining that in a transition state as you're moving from reactant to product, you have a transition state in the middle. So, we have a reactant here. We have a product here. And in order to get that reactant here, a product here, and in order to get there, we have to transition. So we're transitioning from reactant almost at our product. So this is where our carbocation is. It's within that transition state. So once we meet that energy, then we can continue on to the product. So if you remember with our energy diagrams, this is the progress of the reaction, and this is energy. Our reactants start here. We end up with our products, and in the middle is our transition state. So here, with electrophilic addition, right here is where we see our carbocation. So as we're moving from reactants to products, our carbocations in our transition state. So the lower the energy, the faster it goes. Lower the energy, the faster it goes. So since the secondary carbocation is more stable, it's lower energy, it's a faster reaction. Because remember, these little energy diagrams can look like that. Maybe I should put the products a bit higher. That's our activation energy. That's how much energy it takes in order to make that carbocation. So if we have less energy to make that carbocation, the reaction is going to happen a lot faster. Kind of like pushing a car up a hill. So do we want this or do we want something like this, right? It's a bigger hump to get over, and it's going to take longer. But if it's a lower hump to get over, it's going to take less time. Okay. So let's look at how we do this. So when we're talking about flat molecules with trigonal planar atoms, they form a triangle and they're flat. So our starting material, we can have different types of stereochemistry when we're busting up a double bond. So if we're adding a chlorine, when we're busting up this double bond, in the presence of a strong acid, we can throw on another hydrogen there, pop another one off. We can get two different types of stereochemistry. All right. So, first things first, let's talk about what's going on here. How would you explain what's going on in this reaction? With your starting material, so what do we say what the arrows represent? Not electrons, we look at the electron movement. It can also represent attraction. It's always from the perspective of the electrons. So we've got an electron-rich area in this double bond. Is this hydrogen going to be more positive or more negative? More positive. So this electron-rich area is attracted to this more positive hydrogen. Now, since this is a strong acid, what do strong acids do? Do they stay together or do they come completely apart? Completely apart. Weak acids like vinegar, acetic acid, come together and go apart, come together and go apart. So once this hits water, this hydrogen pops right off this chlorine. So it's floating around as a positively charged hydrogen ion. So that full-on positive charge is going to be attracted to all of those electrons, right? Those electrons will be like, hey, positive charge, come on over here. So what happens then is this hydrogen is going to come over here, be attracted to this double bond, and it's going to bust it up. It's going to bust it up. And we have two potential options here. We have the hydrogen that we're adding come out towards us, or it can attach on the backside. And the reason why it can do that is because this is a flat, essentially a flat molecule. It's like flat like the top of a table. It doesn't have, these things aren't coming out at us or going into the board. It's completely flat with the board. So this hydrogen is going to introduce some stereochemistry. This hydrogen can attach on the front side, or it could attach on the back side. And so once it does that, we now have a positively charged carbocation, or a positively charged carbon, because now all of these electrons that were caught up in this bond are now attached to that hydrogen. Y'all see that? We didn't add any new electrons, but we did add a positively charged hydrogen. Did y'all see it okay? We created a bond with this hydrogen, and all we did was use the electrons in this bond. So now we've got this positive charge on this carbon, because the electrons move from here over to here. So this carbon doesn't have that electron anymore. It fulfilled a bond over here with hydrogen. Okay. So now we've got this set up. We can use either one of these. And with that positively charged carbocation, we can now add a chlorine. Chlorine does the same thing. Since this is flat with the board, chlorine can either attach on this side of the molecule or from behind, on the back side of the molecule, which is then going to push this methyl group towards the back or towards the front. So how would you write that out in words? How would you explain that? Well, let's see if we can come up with an answer. All right, I'm going to go over here. I'm going to do some writing. Okay. Okay. Stereochemistry. Electrophilic addition. Stereochemistry, electrophilic addition. Flat molecules, right? If you've got flat molecules, you're going to have to consider stereochemistry when you're dealing with that. Okay, so the first thing we're going to do is look for the double bond. Now, in order to remember what your notes mean, flat molecules mean all lines are flat with the board. So I'm going to draw a picture. I'm going to use this as an example here. Almost squeaky. All right. So then we've got our double bond. We got a hydrogen here. Got something there. And we've got 2 going this way. All lines are flat out with the board. Another example, if this was the case though. No, not always in a ring. We got this, if we got this going on, coming out at the board and going back in the board, right? That is not a flat molecule because these, I got stereochemistry here, right? That's a flat molecule. That is not a flat molecule. So the first thing we do is we look for the double bond, all right? The next thing we do is look for the starting material giving us the hydrogen. Okay? So in this case, we're dealing with a strong acid. Strong acids are great because the hydrogen pops right off. Because hydrogen ion pops off easily, right? Strong acids usually are the ones that give us the hydrogen ions because they pop right off easily. Once they hit water, separate. Hydrogen will break the double bond. Hydrogen's going to break that double bond. And join the carbon. Here's a question. Why would hydrogen join here and not over here? There is a hydrogen here. Yeah, it is electrophilic, that's true. Which one of these could handle a positive charge better? That one here. This one can handle a positive charge better. So this one is going to take on the carbon. This one's going to handle the positive charge better. So in figuring out which carbon will join the carbon that doesn't handle a positive charge so well. The other carbon in the double bond will get positive charge. If secondary, secondary or tertiary. So, but if you are dealing with, if this was secondary, which it is, this one's a tertiary carbon because it's got 1, 2, 3 carbons attached to it. You'll go secondary if the other one's primary, tertiary if the other one's secondary. So the most stable carbon will get the positive charge. The other one is going to get the hydrogen. So Secondary, other is primary. Tertiary, other is secondary. So the most stable carbon with the carbocation gets the positive. The least stable gets the hydrogen. If they're both the same, you can do either one. Yes, so the hydrogen will pop over here, and this one's going to get the positive charge. Yep, you got it. So for positive charge, goes on most stable carbocation. Okay? Most stable carbocation. Now, the hydrogen will present at least 2 stereochemistries. Usually that's pretty much it. You won't get like 3 or anything. I don't think it will. Chemistries. Okay, 2 stereochemistries. You're going to have one coming out. And then you're going to have one going back in the board, right? One coming out and one going back in the board. 6. Now, usually with your electrophilic addition, it's super convenient to make like your strong acid. Then you bring in your nucleophile. Remaining nucleophile, nucleus loving or positive charge loving. Bond with the positive charge carbocation, right? And with that, you've got 2 stereochemistries for that one too. Same situation. You can have one coming out like this. Could be like a Cl or going like this, right? Because of the flat molecule. So in the end, you can have one side where you got a hydrogen coming out, hydrogen going in. To have the other side that's attaching on that carbocation. Got a chlorine coming out and a chlorine going in. So if your 2 groups that you added are on the same side, that's a syn addition. If they're on opposite sides, it's an anti-addition. Okay. All right. So if we're adding a hydrogen and a halogen, usually you're talking about an acid. The mechanism is 2 steps. Markovnikov's rule, unsymmetrical alkenes, your hydrogen bonds to the less substituted carbon to form a more stable carbocation. And then when we look at the stereochemistry, that's Hammond's postulate, syn and an anti-addition occur based on whether the molecule starts out as flat. So these are the main takeaways. E1 mechanism, 2 steps. Remember, E1 mechanism, 2 steps. The rate determining step, how fast it goes, depends on that carbocation stability. So if it's if you're looking at a possible primary or secondary carbocation, secondary is going to be the one that goes faster. Secondary or tertiary, tertiary will be the one that goes faster. And how they attach on for our stereochemistry. It's mostly if the molecule is flat, because then you got 2 sides you got to worry about. How are y'all doing with that? This one is slide 41, if that helps. Okay. The last reaction we're going to talk about, hydration. So if we have water, we've got a double bond. It's a pi bond. Double bonds are pi bonds. So you might see it represented with the little pi symbol. So anytime we're doing a hydration reaction, we're adding water. Hydration is the addition of water to an alkene to form an alcohol. We do this in the presence of a strong acid, hydrogen one side, hydroxyl group on the other. I'm going to erase over here. Similar type of mechanism. Positive charge is going to be on the more stable carbocation. Let me get my marker. Okay. All right. So alkene addition. Hydration. That's a better one. Hydration, alkene hydration, and it makes an alcohol. So we can take a double bonded compound, mix it in some water, add some strong acid, and we end up with an organic alcohol. Anything with a double bond has the potential to become an alcohol. So essentially, we go through the process of an electrophilic addition. E1 is elimination. Boy, I used that wrong. I have like 8 classes I'm teaching this semester. All right. Same type of mechanism. We've got our double bond here. We've got our double bond here, electron-rich area, lots of electrons there. This hydrogen here is slightly positive because this is a polar bond. Hold on, wait a second. That's an H. Oh, that's H2. That's H3O. Oh, this isn't just water. That's water. Okay. They've already added the additional hydrogen. Okay. I see what they're doing. This is after they've added the strong acid. That's not cool. Okay. What? Electrophilic addition to make an alcohol. First thing we do, take alkene and add strong acid plus water. Okay? The water becomes H3O plus. So if our strong acid was HCl, right? This completely separates into hydrogen ions and chlorine ions, right? This hydrogen can jump onto a water to make H3O plus. So we're looking at a little bit of acid-base type of chemistry. Water can act like an acid and it can also act like a base. So this water molecule picks up that hydrogen ion to make H3O. I said E1 last time. That's elimination, not electrophilic. My brain is gone, so don't get that mixed up. So I apologize. Okay, H3O. Now this has hydrogen ion to break the double bond, right? This has the hydrogen ion that we can use to break that double bond. So here, both of these carbons are pretty much the same. So this is a situation where you could put a hydrogen on either side and it'd be correct. This carbon is attached to is two other carbons. This carbon is attached to two other carbons. They both have the same number of hydrogens. They're pretty much equivalent. So if you put the hydrogen on here and the positive on here, that's correct. You can also put it on the other side, hydrogen here and positive here, that's also correct. The thing is, that doesn't make any new stereochemistry. So if you've got a molecule, see if I have it this way, where my hydrogen's here, I could also flip it around this way, and I have the same molecule. That's why it doesn't matter which hydrogen it goes on. It's still going to behave the same. The hydrogen's here, like this, I could flip it over, and it's the same molecule. All I got to do is just turn it over that way. So in flat molecules, make certain that they have different things on both sides. That would affect the stereochemistry. Okay, so here, electron-rich double bond, positively charged hydrogen is on here. All these electrons now form that bond with hydrogen. Positive charge goes on the other carbon. Here is our nucleophile. This oxygen on here has a partial negative charge because it's polar. It's going to attract to that positive charge. So here we've got our OH group is attaching onto that carbon. Oxygen now has that extra hydrogen. Hydrogen can pop right off, join this other water molecule. Now we end up with cyclohexanol. So we have our hydrogen ion breaks the double bond, 3 oxygen on H2O, bonds with the carbon, the positive carbon in the carbocation. Or hydrogen ion pops off of the oxygen bonded carbon and joins joins water in the solution. In solution. So from here, lots of electrons in this double bond. They're attracted to that hydrogen on a hydrogen on that H3O molecule. How did we get H3O? We put a strong acid in there. That strong acid separated. That hydrogen joined that water, gave us H3O. That's where our hydrogen came from that can break that double bond. Now the electrons in this double bond shift over to form a bond with hydrogen. Have a positive charge on this carbon here, so it's carbocation. The oxygen on here is attracted to that positive charge because it's polar, right? Slightly negative charge. It forms a bond with that carbon. So electrons that it had here as a lone pair have now made a formal bond with that oxygen. So here's this extra hydrogen here. Oxygen will just take all of the electrons in that bond. Hydrogen becomes more positive charged. Another water molecule picks it right off. And now we end up with our organic alcohol. It's a lot. I know, it is a lot. I truly, really do feel your pain, because when I took this class, I thought the person teaching it was speaking a new language. It might as well have been baby talk. Like, what is this? Okay. So let's look at we can use other alcohols for electrophilic addition, not just water, anything with an OH. Just remember that if we're trying to make an alcohol a leaving group, you always have to have the presence of a strong acid, because you have to have extra hydrogens to make it a good leaving group, right? Alrighty. I think we talked a little bit already about halogenation. We can take, this would be an example of bromine, like Br2, Cl2, I2. We wouldn't really use fluorine so much, but you could take 2 chlorines or 2 bromines, blast it with a little bit of light. It'll split those in 2 individual ions, and they can bust up a double bond. Huh? Light? Y'all ever notice that iodine is kept in like brown bottles? Yep, it's light reactive. I mean, let's take a moment and think about how cool that is. All right, I'm going to erase right here. Ooh. People forget that light has energy. You know, light has energy. And you can have things that happen and change and rearrange just by hitting it with light. So usually when I make a bromine solution, or bromine water is what it's called, you have to store it in something dark. So one of the things that happens with chlorine and bromine when we're doing halogenation of alkenes. Bromine is yellow. So what happens with bromine? Let me put in my lone pairs. Okay. So my light's going to be red, I guess. Light can come, bust up that single bond pretty easily. Then you end up with this neutral form of bromine. Now, what do we know about halogens when they're in their neutral form? Why is chlorine gas bad for you? Why does it kill you when you breathe it? You ever think about that? Here's the thing. Halogens without a full set of 8 electrons are highly reactive. This is one of the things that I talk about in my Chem 1 class. Chlorine gas by itself will kill you. Horrible. It's a horrible way to die because once chlorine gas hits light, it can separate into individual atoms like bromine can. And when you breathe it in, it's going to immediately start busting up double bonds in your lungs. You're going to have halogenation addition all over the place. Now, if you've looked at anything, like any kind of organic molecule, pretty much all of them have double bonds somewhere, right? Hormones, proteins in your body. Double bonds are essential for altering the structure of different molecules. So, in this form, this will go and bust up all of the double bonds in your lungs. Starts there, then your lungs don't function. Oxygen doesn't get to the rest of your body. Then, you could have bromine that's passing over those membranes, breaking up more double bonds within your blood. It's terrible. Y'all don't want that. It's terrible. It's like a war crime to use chlorine gas. It's like terrible. So, but when you pair chlorine up with something like sodium, it's fine. We use it in salt. We use it for our French fries. Sodium by itself, sodium metal, if you were to chew on that, it would blow off half your face. Sodium does not like to have that electron. Halogens need that electron. So they're like two toxic friends that you have, but when you put them together, they act just fine, right? You can only hang out with certain people if another person's around. That's the way that I think about it. But they're highly reactive. So when we do these light reactions, we can use chlorine and bromine, and they'll just go bam right on either side of that double bond. And it happens quickly. It happens quickly. So let me see. I don't think. Polarizable. There's this one here. We can have this is just the mechanism for it. It's a cross here. The halogens tend to add on opposite sides. So something like this. If you're dealing with something that isn't a ring. Oh, sorry. Where was it? Here we go. You're dealing with a symmetrical alkene. The halogens are going to add on opposite sides. Why do you think that is? Farther apart, electrons don't like to be close together. Halogens are huge, so they're bulky. So if you've got a symmetrical double bond here, where you got both sides kind of look the same, you're going to have opposite ends where those halogens are going to form. Okay? If it's not symmetrical, I can cut this way and it's not the same, right? I could cut this way, it's still not the same. This is not a symmetrical situation. Here, it's a ring. It is technically symmetrical if I go across here, but your only option is to add them on each one of these carbons. Same here. This is our only option. We don't have any other options. We can go on opposite ends on something like this. You're not going to see a bromine go on the inside of a ring. Why? There's other electrons here, and it's freaking huge. Bromines are big old atoms. They're going to want to be on the outside. They've got a lot of electrons on the outside of them. They've got all those lone pairs. So they're going to go as far out as they can. So things to remember with halogenation, okay? If you're using 2 chlorines or 2 bromines to have a reaction occur, this is going to be what your starting is, and these are going to be what your products are. Pay attention to the symmetry of the molecule and think through, where can I put these halogens to where they're the furthest away from each other and have the most space? Because that's going to be the priority. Where can I put, this was 2 chlorines, where can I put these things to where they're the furthest away from each other and have the most space? Opposite ends, right? No, because this could be down here and this be the top. I could just flip it over and it's the same molecule, right? How are y'all doing with that? Well, that's just one thing. So the good news is there's other things that you can look at. I think that's all I'm going to cover on that one. That's it. That's it. So the addition reactions, where we looked at stereochemistry with the flat molecules that are not symmetrical. We looked at alkene hydration, where we can turn a double bond into an alcohol. And then we also looked at halogenation. So let me write up our sum ups on here. And then next class, we'll just spend the whole class working through a quiz that'll look similar to your first test. How does that sound? That sounds amazing. Okay, well, that's good. All right. So main takeaways. Okay, we did electrophilic addition. We did electrophilic addition. We did it with strong acid. We did asymmetric. There should be 2 M's there, I think. I don't know how to spell asymmetric. It's 2 S's, 2 M's, I think. I don't know. Y'all know what I'm talking about. That looks like it's not correct. Those 2 S's there turn it into a different word, I think. I don't know. It's okay. Asymmetric, flat alkenes, right? We looked at that. That's what that is. And mostly with 2 M's, 1 S. See, I thought so. There we go. Okay. Then here we, huh? I can spell science words mostly, like easy science words I can't spell. The stereochemistry for that, we looked at whether it goes in the board or it goes out of the board, right? We looked at hydration of alkenes. We looked at it in terms of strong acid and water. So something like HCl, H2SO4 if we want to do that. Well, no, it would be HCl. Yes, that's fine. Any of those things. This is how we make organic alcohols, right? How we make organic alcohols. Then we talked about halogenation of alkenes. We use bust up X-X. So that's usually Br, or Cl, right? And then they add to the double bond. And I'm going to put a little asterisk right here and say halogens are bulky. So they're big atoms. And they add to positions furthest away from each other, but across that double bond. There we go. Halogens are bulky and they add to positions furthest away from each other. How are y'all doing with that? That's a lot. Okay, so your quiz. I'm going to put together a quiz that we're just going to work on the whole class period on Thursday. And I'll just put together questions that are associated with these things here. So this is my checklist that I'm using. We had our goals for review. I probably, if I were to look at it like a 30-question quiz, I'm probably not even that much. If each one was just a question, that would be then you look at functional groups, general. Say I'm going to probably have 10 questions out of here for goals of review. Probably pull 10 questions for there. And then probably 5 here and 10 here. So 10 for out of review, 10 out of 9, and 5 out of 10. So I'll put together a quiz that follows 10 out of there, 10 out of here, and 5 out of here. And then we'll just spend the whole class period working on that quiz in groups. And then I'll grade them and give you the answers, and you can use that to kind of help you study. Does that sound good? Okay. Well, that's all I got for today. Let me stop my live stream. Oh, good, the mic is working. All right.